All right, thank you, everyone, and greetings from Oregon. Thank you so much for making it out today. So today we're just going to give an update on our working group. So we just were approved and started our activities in last September. And so I'm just going to summarize kind of what we've been up to and then kind of where we're going right now. So first, I'd like to thank the US CLIVAR for sponsoring our working group. And I'd also like to thank very much our membership, our US members and our international contributing members who you see here. And especially want to thank those. So we've had a number of telecons and other activities that have stretched time zone boundaries. And so I really want to, I really appreciate everyone's willingness to volunteer their time for to kind of for our working group. So I just want to remind everyone what our prime objectives were. So we might have some people on the line that have not been familiarized or are not familiar with our working group or what our goals are. So our main goal is to formulate and coordinate observational and modeling efforts to quantify the ocean mesoscale and frontal scale air-sea interaction coupled processes and evaluate their impacts on Earth's climate and hydrological cycle. And so there's been a lot of work at trying to quantify this from a variety of ways through observations and models. The last 10 years has seen a very big increase in the capabilities of models to resolve very fine scale spatial processes. And slowly we are getting catching the observations up to that. And and we're starting to see that there's quite an quite a strong impact on ocean mesoscale variability and frontal scale variability on the large scale, and a lot of different impacts. So this is actually quite an exciting time. And so one of the new things our working group is really trying to kind of wrap our heads around is, trying to take the coupling that we've observed on the mesoscale and really describe how it's affecting Earth's large scale climate. So part of our objectives or part of our tasks and activities that we're going to do to achieve this goal is during year one, we want to produce a review paper that synthesizes the current understanding and bring out the open questions regarding mechanisms of ocean atmosphere coupling and impacts and things like that. And some of the things that we are working on in the review paper are the impacts on large-scale atmospheric circulation and oceanic circulation, Earth's hydrologic cycle, and ocean biogeochemistry, among several others as well. And we have some very good expertise among our working group members in all these areas. And it's been really a great pleasure in the little time that we've had to work together so far. So I'm really hopeful that we'll make some progress in this area. The second thing we want to do is develop diagnostic frameworks to analyze models and observations. And one of the things that we've seen in a lot of current work is there's a lot of different ways of looking at this. And so, and in some cases, the different ways that we analyze data and what data sets we look at actually influences the conclusions we come to. So we want to kind of analyze how we, look at models and observations and what we use to do that. And finally, we want to identify any consensus on uncertainties and directions forward for observing systems and modeling. And so any in situ satellite observations coming up, as there are requirements for SST or surface winds or surface currents and things like that to understand this coupled process better. We want to motivate coordinated process-oriented modeling and observation studies. And we like to broker community efforts from previous CLIVAR working groups on very related topics. First thing I want to do is, just for those who are a little bit unfamiliar, is just define the oceanic mesoscale. So ocean mesoscale features have length scales of roughly 50 to 1,000 kilometers. And sometimes I use this map to kind of visualize what this is. So this is the Golis return current off of South Africa. And what I've done is spatially high pass filtered the sea surface temperature field there. And so you get a lot of these standing meanders and eddies in the flow field. And so, sometimes it's hard to visualize how big those are. They look kind of small. But if you overlay the states of Texas and Oregon on them, those are the kind of length scales that we're talking about when we talk about the oceanic mesoscale here. So these ocean mesoscale features are associated with a variety of processes such as meanders and large-scale currents of filaments, for instance, in upwelling zones along coasts, and as well as propagating eddies that can occur anywhere in the ocean, from on the continental shelf to the open ocean, etc. And ocean mesoscale variability is typically enhanced near western boundary currents, not always, but typically. And propagating eddies are ubiquitous in much of the ocean. They often form in a variety of places and propagate usually westward. And those eddies can also have a good influence on the atmosphere too. So we also talk about, so in our title, we have mesoscale and frontal scale. So frontal zones typically are associated with western boundary currents and their extensions. And they tend to be more semi-permanent, although they may fluctuate in position and strength. And the length scale that's typically defined frontal zones as a mesoscale feature is usually what's across the front there. And so these are often the most well-studied frontal zones in the ocean in mid-latitudes. And so you have the Gulf Stream, the Kuroshio, the Golis return current, and the Brazil-Mont Benavides confluence in the South Atlantic. So these are quite important. And I also want to point out that, so this is like a time average map. So there's also variability that can happen downstream of the major currents in their extension regions that at times can also be as significant as well. So these are all kind of places where we will expect to provide quite a bit of our focus on here. So now that I've done that, I just wanted to give a brief summary of what we've done as a working group so far. So like I said, we convened in September 2019 and began team building and getting our roster of members together. And so we've held a couple telecons, usually bi-monthly, so once every 2 months or so on average. And one of the big activities we did was we co-sponsored an Ocean Science 2020 session in San Diego this year, right before the world turned off. And we also had an in-person meeting on the Tuesday evening, which was graciously hosted with dinner, which was awesome. Thank you. And during that meeting, it was we met for about 2 hours, and it was extremely productive. We had a few people join online as well, or on Telecon, and we started generating or continued generating our outline for our review paper, which I'll talk about in more detail in a bit. We discussed some plans for our community workshop that we want to have near the end of year 2 or beginning year 3. And we also kind of helped define the scope of our working group activities. And just to make the week even more exciting, many of us attended the Service Currents workshop that was held at Scripps that following weekend. And then we also formed topical subgroups that we identified some areas of particular importance, and we'll talk a little bit more about it next. So these topical subgroups, sorry. Okay, I don't know why my slide's like that, but we'll go with it. So these topical subgroups, we chose 6, and that we kind of felt were the most important areas that we wanted to focus on. So these include ocean circulation biogeochemistry, diagnostic metrics of air-sea coupling, atmospheric boundary layer processes, mechanisms for predictability, air-sea flux parameterizations, and dynamics of atmospheric responses to ocean mesoscale variability. And we had subgroup leaders, which are underlined as well. And we have a really good mix of people who are, people are in a couple different subgroups. And so this is, kind of mixing up the interdisciplinary, or, providing a real interdisciplinary perspective on some of these topics that is really kind of enriching the conversation here. So our Ocean Sciences 2020 session, so we sponsored a session, mesoscale and submesoscale ocean-atmosphere interactions and influence on Earth's climate. And a couple of us on the working group were co-chairs for the session. And we were limited to 8 oral presentations, but we had 28 posters. So it was a fairly successful in terms of numbers, but it was really great. We had a wide diversity of talks that were very relevant and thought-provoking, and really was really great for seeding some of the current knowledge for our review paper that we're hoping to get done during year 1. So this review paper is going to be one of our main goals for our year 1 activities. And part of the process of doing this review paper is to become familiar with the current state of our knowledge of the air-sea coupling at the ocean mesoscale and how it's impacting the variety of processes that we've outlined before. So, so this review paper will be kind of in the same kind of genre as some of the previous review papers, like Justin Small's review paper and a few others that have come out of CLIVAR working groups in the last 10 or 15 years. And we hope to just summarize kind of the observational modeling evidence demonstrating the ocean-atmosphere coupling on the mesoscale, provide some summaries of physical mechanisms that are govern this coupling. And then we'd really like to get at the impacts of the coupling on climate, precipitation, biogeochemistry, large-scale ocean atmospheric circulation, among other things. And really, yeah, because I think there are some really great impacts that will really enrich the study of like the physical mechanisms and other things. And we also want to kind of summarize some of the approaches and techniques that have been used to diagnose and analyze the mesoscale coupling, including like spatial filtering, high-pass filtering, temporal averaging, and other things like that. And then also look at intermodal comparisons and evaluating models with observations. What kind of observations are available in the historical data records? What kind of model simulations have been done? And things like that, and what have they found? So so in our kind of doing our review paper outline, we've identified kind of 6 sections more or less, and so I put them here as themes, and I'm going to try to quickly go through these 6 themes, and just to give you a flavor of what we'll be focusing on during year 1. The first one is, of course, why is the mesoscale and frontal scale important? Why are these, why are we looking at these interactions at the scale? What is, defining the scale, contrasting it with other frameworks of ocean-atmosphere interaction, things like that. The second one is just look at impacts of eddies and fronts on surface heat, freshwater, momentum fluxes. So the fluxes are kind of what communicates the ocean to the atmosphere and vice versa. The third one is the local atmospheric boundary layer response to mesoscale and frontal scale variability. The fourth is deep tropospheric and large scale atmospheric responses to ocean mesoscale variability. So this will govern things like a non-local response or changes in storm track, changes in large scale circulation that that is caused by mesoscale variability in different places. So if like a western boundary current can change the jet stream location or the storm track location downstream, try to assess those impacts. The fifth one is the feedback to the atmospheric mesoscale response back onto the ocean, and how the ocean responds and just the coupled feedback process there. And the last one is quite an important one, is the implications for future research and understanding as well. So like I said, theme 1, we're just going to define our traditional paradigm of mesoscale and frontal scale interactions, how different people have defined it, and try to come up with a common definition. Also identify sources of coupled ocean atmosphere variability, so things like the western boundary currents, eddies, etc. And and just give a summary of impacts of local coupling to larger scale effects here, which I think is a very important part of what we're doing. The second one is looking more a little more narrowly at the surface fluxes. So we have sea surface temperature that and surface currents that can influence the surface fluxes in very profound ways. And so we're going to be looking at needs for observational estimates, accuracy requirements, wave current effects on fluxes, and really looking strongly at the surface wind stress and looking at the importance of both the wind SST coupling and the incorporation of surface currents and surface wave feedbacks onto it. The third theme is just looking at the local atmospheric boundary layer response. So this is just describing how the atmospheric boundary layer, which is typically the lowest kilometer or so part of the atmosphere, is changed in locations of mesoscale SST variability. And the atmospheric boundary layer will communicate the surface response to the deeper atmosphere, and this is an important mediary in how the mesoscale SST variability can influence the large-scale climate. And so this is a very important process that for models to get right, and so we want to try to do what we can to synthesize what this current state of the knowledge is and what remaining, what issues remain and what we need going forward. So by the atmospheric boundary layer, things like winds, turbulence, its depth, clouds, precipitation, its pressure structure, formation of interterminal boundary layers, and of course the surface wind stress. And of course the main forcing agent is SST, but ocean surface currents and waves also play an important role that's come out in work in the last 5 or 10 years. And we're going to look at a lot of different observational modeling studies. And the other thing we're going to look at too is the space and time scale dependence of the coupling. So if you have a Texas-sized SST perturbation, the coupling might be different than if you have a Rhode Island size or a continental-sized SST perturbation. So a lot of this work is, or some of this work is motivated by this correlation between surface wind and SST on the ocean mesoscale. And so this just shows a map of the correlation coefficient between surface wind and SST that both have been spatially high pass filtered to focus on variability smaller than about 1,000 kilometers in length scale. And the red areas all indicate a positive correlation, so faster winds over warmer water, slower winds over colder water. And this really highlights the regions that would tend to focus on, which are the western boundary currents. There's also a big region in the equatorial Pacific, and then also in the Southern Ocean. And so these correlations tend to be strongest in regions with strong currents and eddy-rich regions, and those both have very large SST gradients there. So surface currents are also quite important for the modeling study, and so this is just highlighting some work by one of our members, Lionel Renaud, who's done a series of modeling studies showing that if you use in the surface wind stress formulation, if you incorporate surface currents in addition to the surface winds into the models, the ocean that it produces is much more much more realistic in terms of eddy kinetic energy, among other diagnostics. So if you don't incorporate surface currents, you get an ocean that's too energetic in terms of eddy kinetic energy. But if you use the surface feedback here, and he's also shown that in the Gulf Stream region, at least, that the path and variability of the Gulf Stream can change between if you include currents than if you don't include currents. So if you include currents, obviously you get a more realistic Gulf Stream, and this is an issue because a variety of modeling studies, some include current feedback effects and some don't. So our fourth theme that we're going to look at is the deep tropospheric and large-scale atmospheric responses to ocean mesoscale variability. And so this is looking at how things like the Gulf Stream and whatever influences storm tracks, extratropical cyclones, atmospheric fronts, its influence on Earth's climate. And we've had a lot of discussion of what we mean by Earth's climate. And I've listed a couple here as including Earth's hydrological cycle, the climatological mean atmospheric and oceanic circulation. So in this case, you mean something like the variability of the Ferrel cell. So some first order impacts on the first order knowledge of the atmospheric circulation. And then extreme terrestrial hydrological events. So atmospheric rivers, monsoons, droughts, floods, and MJOs. these have all been shown to have, mesoscale SST has been shown to kind of affect all these in some capacity. So, and then also, process is important for climate change. So changes in storm tracks due to changes in western boundary currents, and then meridional heat and moisture fluxes. So kind of the order one process of the atmosphere to determine kind of our state of our climate. And modeling studies have shown that the if you smooth out the Gulf Stream, so these top maps just show a nice study from Kawano Yoshido in 2010. So they did a modeling study just showing if you have a Gulf Stream, and so if you just have a control run where you have a Gulf Stream with its observed temperature gradients, you get a precipitation structure that looks very realistic. So the blue is showing precipitation amount here over an annual cycle. And then if you smooth out the Gulf Stream SST front, so you essentially take out its frontal zone, the precipitation band that's kind of was very compacted over the Gulf Stream now spreads out over a very wide area in the subtropics, and it changes the downstream structure of the precipitation. And so for time, I'll go on. And probably one of the seminal studies by Shishiro Minobe in 2008, who's part of our working group, kind of brought a lot of this to our attention, the effects of this mesoscale air sea coupling on the larger scale climate. And he showed that over the Gulf Stream, you get this nice convergence zone. So this is the surface wind convergence in the time mean. And he theorized that he also showed that there is also a upward vertical velocity zone that's anchored to the surface convergence, and it overlies the Gulf Stream SST frontal zone. And this is where the rain rate happens. And so it was kind of provided a link between the mesoscale SST structure and the deep troposphere. And of course, if you look more closely, that there's downstream impacts as well that he's also, so it's a very big signal. Of course, there's some complications to this simple idea, and one of them is the storm track overlies the Gulf Stream. And so this is just the same thing here. So this shows this convergence zone over the Gulf Stream with contours of the meridional wind variance overlaid. So the meridional wind variance tends to be an indicator of storm track activity. And so you see there's a very high collocation between stronger meridional wind variance or storm track activity with the convergence zone. So essentially the alignment of the Gulf Stream convergence zone with the storm track makes it difficult for us to isolate some of the different processes that are contributing to the atmospheric response. Here, so this is one thing that we're hoping that the working group can provide some insight into. The fifth theme is feedback to the atmospheric mesoscale response onto the ocean. So this includes modulation of ocean energetics, stratification, and vertical fluxes, air-sea carbon exchange and ocean biogeochemical processes, and basin scale ocean transport and baroclinic instability are things we want to look at. And there's been some idealized studies looking at if you include this air-sea coupling in an ocean model. So if you have, so this is was just a modeling study by Jin et al. In 2009, and it showed a upwelling zone kind of in a typical of an eastern boundary current region. And this just shows temperature and colors, so cold along the coast and then warm inland. So if you allow there to be a coupling between the winds and SST in the model, you get a lot less upwelling and a lot less energetic mesoscale eddy field in the ocean than if you don't allow the coupling here. So this is a fairly consistent picture that is showing up time and again in some of these process studies, that it's an important thing to include the mesoscale coupling in ocean simulations. And finally, the last theme is in our review paper is we'd like to have recommendations for funding agencies. And we also want to work on the importance of investment of collaborative working and effectively communicating across disciplines. So, and kind of just enhancing some of this progress by removing communication barriers. And we also would like to try to give some sort of recommendations of best practices of analysis and ways and pathways forward in some of the research. And this might include recommendations for the ocean observing system or modeling, modeling studies, things like that. And then finally, a gap analysis as well. So I'm just going to end with some of our future goals here. So we want to complete the review paper, hopefully by the end of year one, although progress is a little bit slower the last couple of months. We'd like to incorporate some webinars into our telecon rotations. So we also want to begin evaluation of diagnostic tools and metrics suitable for multiple space and timescales and model and observational data sets. We've talked about producing a centralized data repository for the purpose of doing this evaluation and getting a subset of some of the high resolution climate models. We have some great expertise on our working group that has access to a number of state-of-the-art simulations, and can easily get us access for that. We also have expertise on the working group for satellite data, and also in situ boundary layer measurements and flux measurements from aircraft and radio sound data. And we are still we're also deliberating on the timing and of our community workshop in late 2021 or 2022 right here. So with that, I'm finished. So thank you very much, and I'll take any questions.
I have a question. I think, sorry, I joined a little later because I was on another call that went too late. But just looking at these last slides of the future goals, so are you planning to do some comparison or analysis of climate models yourself within the working group? Or your goal is just to create this repository of data for other people to look at?
Yeah, great question. So we are we're hoping to do this kind of in-house within the working group, although we have some limitations on time, of course. But I think we can. I'm pretty sure we can leverage time on existing projects to do some some kind of preliminary analysis for this. And possibly even, if we need a more sophisticated analysis or more data, then, possibly, putting in a proposal to do that.
Okay, thanks.
So you see a question in the chat box. Chris Tykuch asks, do the activities of the working group involve consideration of these processes in the context of the coastal ocean?
Of the global ocean?
Coastal.
Oh, coastal. Oh, yeah, thank you. Yeah, the question is yes. I mean, I highlighted the western boundary currents here, but we're also, the eastern boundary current regions are also within the scope of our, I think, of our working group. Absolutely. Hyodae, do you have anything to say about that?
Yeah. So I think one of the the sub theme of the working group is to look at this airship flux parameterization and boundary layer parameterization in numerical models. And coastal areas are the area where all these land mass and ocean marine air masses collide, and their interactions becomes sort of very strongly emphasized. So I guess those are the area where also ocean mesoscale and frontal scale variabilities can be very strong. It's like eastern boundary. So I think so. Looking at it, the air flux parameterization in these existing models, climate models, and also we have these boundary layer measurements. In situ measurements and satellite observation. So hopefully can use that to improve process understanding of the physics, right? And that can be used for hopefully in a large scale model. And I think that's one way it can make impact on the global climate modeling communities to improve the representation of the airship fluxes with a focus on maybe coastal area or other areas as well. So I think that's one of the key goals of the working group is to look at response and diagnose the response and in the atmosphere to the ocean mesoscale from the models and observations, and try to just represent that in the numerical model through the physics. And that's where like things like wave process can be imported to the coastal ocean as well.
And there was a comment by Justin Small in the chat box saying the Gen et al. Results shown by Larry were for coastal regions.
Yeah.
Oh, yeah. Yeah.
Charlotte says, just a comment. Anish and I will be convening a workshop entitled Tropical Pacific Observing Needs to Advance Process, Understanding, and Representation Models in spring or summer 2021 that will likely have subject overlap with your planned workshop. We should keep each other informed of our plans to maximize the benefits of each workshop.
Oh, awesome. Thank you. That would be great.
So that's both for Western Pacific and Eastern Pacific as well, or just is there any geographical area within the Pacific or tropical oceans? And that's the workshop? Okay.
It's for the tropical Pacific, yes, the Pan-Pacific, Pan-Tropic.
Okay, so whole area, okay.
Yeah. So yeah, following up on that, I also wanted to mention that there's interest in the PISMET panel in Charlotte, and I don't know if Kevin's online, or some of the other panelists can chime in. This follows on from a summit last year. So Hyodae, I think you were on the panel then. The idea of exploring the development of a focus process study on the Gulf Stream. And so I'm kind of curious in terms of, for your workshop, as you start to look forward in the development of that workshop, do you envision regional foci, or looking at say the western boundary currents versus the coastal regions and some of the challenges, or the Southern Ocean and some of the regional challenges that exist regarding air-sea interactions that might involve different sets of processes?
Oh yeah, that's a great question too. So it's possible we might do that. We haven't discussed very much. One thing is that if you focus on one region, it's kind of predominantly or exclusively, you might get a kind of a skewed version, or a skewed message on what the impacts of the air-sea coupling. One thing is over the Gulf Stream. Gulf Stream is a very unique place. Has some big differences from the Kuroshio or from some of the other western boundary current regions, and of course, all the western boundary current regions are quite a bit different from the eastern boundary current regions in terms of the coupling. So yeah, so it's something I think we should consider. But in my viewpoint, there's some big differences between regions that might not generalize to the global ocean.
Okay.
Yeah, and that's in fact one of the challenges that we have in the working group is that when you look at the air-sea process over the whichever area where we have very strong ocean mesoscale eddies and strong air coupling, which is not just in the western boundary current. It's like in the tropical ocean as well. We have very, very strong coupling at the scale. I guess we try to find a kind of science plan that encompasses all this area of strong air-sea coupling, and that's hard. And although I really like the idea of having a focus workshop on the Gulf Stream, which I really support, but I guess I don't know how we can engage this working group activity into this. We have to think about it a little bit. Yeah.
Yeah, right. And I didn't mean to imply that your workshop should focus on that specific region, but rather, if we're going to be developing something, we can develop an activity in the Gulf Stream that, understanding how that can connect up with your workshop, similar to the tropical Pacific one that's being planned for this next year.
That's a great idea. That would work very well, I think, and some of our work could definitely inform that or be quite complementary.
I'd also point out, if I can, that for Fall AGU, there is a session on large-scale atmosphere, this is large scale, atmosphere, ocean dynamics, and climate variability and climate change, being convened by Robert Wills, Joanna Maya, Gally Burles, and Elizabeth Maroon. So keep that in view. There might be some interconnection with the work of the working group here too. So it might be helpful for us to be amplifying that opportunity. Abstracts are due at the end of July.
Yeah, so I think the results that you presented about the changes in the Gulf Stream path, depending on the capturing the mesoscale eddies, I think that's a very, very powerful result. Although not all the high resolution model necessarily solve the separation problem. So you need the high resolution to solve the mesoscale eddies, but you may not necessarily solve the problem. So I wonder what are the key ingredients for actually be impactful on the Gulf Stream path.
So my understanding is that yeah, I guess like Antonietta was saying this, if you have a higher resolution, you tend to assume the Gulf Stream separation and flow stability will be improved, but actually that's quite the opposite because we have two strong eddies, two long-lived eddies, and two unstable mesoscale western boundary current. So ocean model tend to tune that with a viscosity, right? Artificial damping, or some model even just artificially reduce the wind stress by 20–30% just to get the right amount of kinetic energy level in the ocean. It's so artificial tuning of within the model. I think what Lionel is showing, and some of my study also have been shown that this ocean current actually does all the work, the physical work. So you don't really need this artificial damping process in the ocean, viscosity, things like that, because the ocean current actually reduce the wind work and that transfer the energy actually back to the atmosphere. So change the wind profile as well a little bit in the boundary of the atmosphere. But most of the work is actually just reduce the amount of energy that goes into the ocean from the wind. And that has a cascade of the response in the ocean, sort of energies, just energy propagation within the range of spatial scale in the ocean. So I guess this is this idea is not new, but it's been done like many decades, like effect of surface current and the numerical model. But I guess what is showing that when you resolve these very strong mesoscale eddies in the high resolution climate model, this effect can be even more important because the bias is so confound. It's like so large to energetic eddy variability. That are very common in many numerical models.
Any final questions for Larry and Hyodae? All right, I don't hear anyone or see anything in the chat, so I think Larry did a really great job at being thorough with his presentation. So thank you to Larry and Hyodae for representing the Air-Sea Interactions Working Group. This wraps up our working group webinar series for now, which I will miss having an excuse to talk to all of our working group co-chairs like what we've had over the past few weeks, but I'm sure we'll hear updates from you guys periodically over the next few months as things start getting underway again. So thank you everyone for joining.